In this lesson, we're going to look at applications of exponential functions. Specifically, we're going to look at population models. So population models often follow growth or decay rates. So in this function here, it's just another way of writing your general function, which is y equals a, which is your initial value times your base, to the x power. So since the p sub 0, or p naught, is in the a spot, that's your initial population, whatever it's starting at. R is the rate at which your population is growing or declining. T is your time. And P of t would just be your final population. Okay, just reminding you again that R is your growth rate or your decay rate, and 1 plus R is your growth or decay factor. That'll help you with these word problems. So we're going to write an exponential function to model the situation, and then we will use that model to answer some questions. So it says a new snowmobile costs $4,200. The value of a snowmobile decreases by 10% each year. So first, write an exponential decay model giving the snowmobile's value in dollars after t years. Okay, so I'm going to go with, this one's not really a population model. I'd just say this is exponential. I'm going to say my y is v for value, and I'm going to say t is my independent. So v of t, you could just use y equals if you want, equals the initial value of the snowmobile was $4,200, and it's decreasing by 10%. So that's my rate. So it's going to be 1 minus 10% inside the base raised to the t power, which I can clean up a little bit and write as 4,200 times 0.9 to the t power. We're going to use this now to estimate the value after 3 years, which means I'm just plugging in 3 everywhere there is a t. And I can just type this into my calculator, and I get that v of 3 is $3,061.80 to the nearest penny. Now we're going to determine the value of the when the value of the snowmobile will be $2,500. So that means I'm plugging in 2,500 for v of t. However, you haven't learned how to get a variable out of an exponent spot yet. We're going to need to learn about logarithms first. So we're going to use a graph to do this. So what we're going to do is we're going to let one value be, or one equation be y equals 2,500, and the other will be my function 4,200 times 0.9 to the t. Well, in the graphing calculator, you would have to use x. And we're going to find where these two things intersect. And when I find where these two things intersect on the graphing calculator, I get that they intersect at 4.89, approximately 4.89 years. In example 2, it says in 1996 there were 2,573 computer viruses and other computer incidents. During the next 7 years, the number of incidents increased by about 92% each year. Write an exponential growth model giving the number n of incidents t years after 1996. So the number of incidents is going to be equal to, so the number of incidents would equal, the initial value is that there was 2,573 viruses and incidents, but that's increasing by 92%. So my rate's 0.92 raised to the t power, where t is in years. So I could also write this with my growth factor of 1.92 to the t. About how many incidents were there in 2003? Well, let's see. So 2003 would be 7 years after 1996. So I'm going to plug in 7 into my function. And I can just put that in the graphing calculator, and I get approximately 247,485 incidents. Example 3 says a sample contains 1,000 counts of bacteria. Bacteria doubles every 20 minutes, which is gross. At this rate, how many counts of bacteria will there be in 3 hours? So this is definitely a population model. It's growing very quickly. So I'm going to say my population, or P of T, or T is going to be my time in hours. Begin with 1,000, and the bacteria doubles. Okay, so that is my growth factor. So here's how I'm going to set up my exponents. Since bacteria doubles every 20 minutes and my time is in hours, how many times will it double per hour? Well, it's going to double 3 times, right? Because there would be 3 sets of 20 minutes in 60 minutes. So it's going to be raised to the 3 times t power. So now I'm asked how many times, or at this rate, how many counts of bacteria will there be in 3 hours? So I can just plug 3 into my function. So I'd have 3 times 3, which would be 9 right here. And then I put that into my calculator, and I get P of 3 gives me 512,000 counts of bacteria. Wash your hands. Last example is another population example. A state's population is declining at a rate of 2.6% annually. The state currently has a population of approximately 11 million people. Write an exponential function that models this population in years. So again, I'm going to use P of T, my initial value, 11 million, and my population is declining 2.6% each year. So just write this out one more time, simplifying my base to make it 0.974. So then we are asked, if the population continues to decline at this rate, what would we expect the population to be in 15 years? And then again in 30 years. So go ahead, pause, put that into your function, check your values.